To all, on behalf of IGNOR Regional Center Bhubaneswar, I welcome you all to this online platform on online class of your MCH-02 paper of PGPSC program. And yesterday, we have discussed the first block of MCH-02, which include your separation techniques, different physical and chemical or electro migration of different constituent of a mixture, and depending upon their different physical and chemical properties they get separated from each other in a mixture. And under physical method we have discussed filtration, distillation, fractional distillation, then some solvent extraction methods. So, we have two units: solvent extraction one and solvent extraction two, where we had used some extractants, chelating agents, complexometric titration or complexometric methods, followed by diluents and modifiers. So these things we have already discussed, and today we discuss the most advanced technique of separation method, which is all about your chromatography, which was discovered by Michael Swell in 18th century, um, during the pigment separation of during the chlorophyll separation of different pigments in a leaf sample, leaf extract. So Michael Swell was regarded as the father of chromatography, and in 1952, I think two scientists, Martin and Poe, got Nobel Prize in chromatographic phenomena, and this is the broad outline or structure or content of this unit. This is a general principle of chromatography, and it includes your definition, classification, what is liquid chromatography, gas, supercritical, fluid chromatography, followed by illusion in column, migration rates, distribution constant, retention time, retention factor, selectivity factor, shapes of peaks, concept of theoretical plates, rate theory, eddy diffusion term, longitudinal diffusion term, non-equilibrium and mass transfer term, band, diameter, plot and zone broadening. After that, resolution and so on. So it was discovered by Michael Swell in 1906. It is the year when he tried to separate different separate chlorophyll or different pigments in a leaf extract sample. So the work he was done, it includes liquid solid chromatography, where liquid solution is treated as the mobile phase, and the solid adsorbent is known as the stationary phase. So whenever liquid solid adsorption chromatography is there, the physical method that includes your um, adsorption is carried out. Okay. So after that in 1952, here it is written, 1952, Martin and Sims were recognized and they were awarded the Nobel Prize in Chromatographic Science. Then we have different type of chromatography techniques depending on the type of separation we have made and depending upon the what type of chromatogram we are using. And what is the mobile phase as well as the stationary phase we have taken for that separation. So in 1959, gel filtration chromatography, 1960 high performance liquid chromatography, which is in short is known as HPLC, high performance liquid chromatography, followed by supercritical fluid chromatography. So these are all advanced techniques which are mostly used for the separation of different components in a mixture. Then we have the definition and classification. So in definition we have chromatography is a method of separation in which components to be separated are distributed between two phases. One is stationary and another is mobile phase. As already we have uh, explained that stationary phase is your static phase and mobile phase is your dynamic phase. So this the dynamic phase or mobile phase is spread over the static phase with different adsorption or your chemical bonding or attraction towards the different component present in the mixture. So the component which is having strong attraction towards the mobile phase or towards the stationary phase will be at the bottom, and the pigment which is having the less attraction towards the stationary phase, it will be go up. So this is how one by one your different components in a mixture gets separated. So the classification, we have the situation spelled out above. The chromatograph is classified with the shape of the solid support, that is stationary phase, the nature of the mobile phase, it is the dynamic phase, the mechanism responsible, whether it is adsorption, whether it is chemical bonding, whether it is van der Waals attraction, but depending upon different type of mechanism involved in separation of different components in a mixture, the classification of chromatography takes place accordingly. If you go by the shape of the solid support, the first one, there will be three-dimensional, that will be column chromatography, two-dimensional, this may be thin layer chromatography or paper chromatography. So in three-dimensional, we have a column chromatography where a cylindrical glass tube is taken, and the different the mixture with silica gel was placed inside the column, and one solvent is in terms of your mobile phase was passed through that stationary phase, and then depending on its the reaction or bonding, different components get separated. Just see the column chromatography. So this is the column chromatography we have. Just see here. Yes, this one. So this is the column chromatography where a column is used. Okay. So here, just see here. What happened? This is a mixture. This is a mixture, and it is passed through the silica gel layer, and after addition of the suitable solvent, then the components gets separated according to their attraction or chemical bonding with the solvent. So this is the column chromatography. Then similarly we have thin layer chromatography and your paper chromatography. Paper chromatography already discussed. This is a thin layer chromatography where one PLC paper is used, and your sample is placed at the reference point, and when it is placed in a suitable solvent, then the different pigments along with the mobile phase goes off according to their attraction or chemical bonding, and accordingly your retention factor and retention time is calculated. So this is your PLC. And similarly, your paper chromatography is there, which is your two-dimensional chromatography, and column is your three-dimensional. Then this is too simple to classification and doesn't take into consideration the nature of the mobile phase and the process responsible for separation. If the classification is done purely on the basis of nature of mobile phase, there will be three types of chromatography: liquid, gas, and supercritical fluid chromatography. So if we take the second one, that is the nature of mobile phase, then with the mobile phase may be liquid, so liquid chromatography. If it is a gas, gas chromatography, or supercritical fluid, this will be SFC, supercritical fluid chromatography. So on the basis of stationary phase, it may be two types, two-dimensional and three-dimensional. Under two-dimensional, we have thin layer and paper chromatography, and under three-dimensional, we have column chromatography. So on the basis of mobile phase, we have the phase or the state of the mobile phase. That is, if it is a liquid mobile phase, then the chromatography is LC, that is liquid chromatography. If it is gas, this will be GC, gas chromatography. And if it is supercritical fluid, then SFC, supercritical fluid chromatography. Then, according to the mechanism involved, there is the type of interaction that will happen between happening between stationary phase and mobile phase. There are four types, distinct types. What are they? They may be adsorption, that is liquid solid, maybe partition, liquid liquid, ion exchange between electrolytes, and size exclusion, that is type of that depends on the dimension of the constituent present in a mixture. So depending upon the mechanism involved, the chromatography is a primarily it is of four types: adsorption, partition, ion exchange, and side exclusion. So in adsorption, what happens? This is the primary or basic mechanism of the liquid solid chromatography (LSC), where the liquid or the liquid is acts as the adsorbate and the solid is acts as the adsorbent. So that is the stationary phase and liquid phase. And the phenomenon that involved in this separation is the adsorption phenomenon. So depending on this and the adsorption, the different components gets attached to the stationary phase, and accordingly what happens, there will be separation depending on their retention time and retention factor. So the partition, it is about liquid chromatography. So in this partition chromatography, one liquid is acts as stationary phase, whereas the other liquid is acts as the mobile phase, and accordingly their retention factor is calculated. Ion exchange, where there will be anion exchanger and cation exchanger. And this ion exchange chromatography, it is primarily used in demineralized water in large scale, and at the end we have side exclusion chromatography, where different components in a mixture are separated with respect to their dimension or with respect to their size. Then we have the things here, it is written there are three types of chromatography technique, that is liquid chromatography, gas chromatography, and supercritical fluid chromatography, which is classified based on the type of mobile phase. Okay. Then the first one is liquid chromatography. So in liquid chromatography, it may be of two types, that is liquid solid chromatography or liquid chromatography. If it is a liquid solid chromatography, then the mechanism involved is adsorption. But if it is liquid chromatography, then the mechanism involved is your partition. Okay. So liquid chromatography, where both the stationary and the solid phase are liquid, is known as liquid partition chromatography. The support holding the liquid can be in the form of three-dimension or two-dimension. In the two-dimensional form, the mobile phase can move from top to bottom or bottom to top, thus known as descending or ascending chromatography. That means here one liquid it acts as mobile phase, whereas the other liquid acts as the solid phase. The liquid which is acts as the solid phase stationary phase is supported by holding the liquid with a three-dimensional column or two-dimensional thin layer or paper, and with the paper or thin layer column, thin layer chromatography paper or chromatography paper, it is just dipped in a solvent, then it is known as the ascending chromatography from bottom to up. But when your paper or thin layer paper is hanging out at the top and it is uh, towards the gravity, then what happened? Then what happened? The constituent particles or the constituents are separated from top to bottom. So this is now known as the descending. So if the paper is hanged, then it is descending. If the paper is inside the solvent or it is put inside the solvent, then it is known as the ascending chromatography. So in both the cases, ascending and descending, the constituent particles get separated depending on the retention time or retention factor. And this retention time and retention factor is primarily based on the adsorption or partition phenomenon between the mobile phase and the stationary phase of the different components in a mixture. So conventionally, the highly polar solvent, here it is written, highly polar solvent is held on the support and mobile phase relatively non-polar. This is known as normal phase chromatography. Okay. If the stationary phase is non-polar and the mobile phase is polar, it is termed as inverse phase chromatography. So there are, according to polarity, we have two types of chromatography: normal phase and reverse phase. In normal phase, the stationary phase is polar and the mobile phase is non-polar. But in reverse phase chromatography, the stationary phase is non-polar and the mobile phase is polar. Then we have the extraction chromatography where the different constituent or pigments get separated and it can be extracted through proper mechanism. An important modification in terms of stationary phase is introduction by loading the extractant used for solvent extraction on a hydrophobized inner support or irrigating the support with aqueous solvent. This is known as extraction chromatography. At this point, it may be important to introduce liquid chromatography on bonded phase. So this is your liquid chromatography. So this is some examples where we have the mobile phase acts as the stationary and another mobile phase acts as the mobile phase. Then one liquid acts as the stationary phase and the second liquid it acts as the mobile phase. And here the phenomenon is partition chromatography, and here rigid silica or silica based, which was already pointed out that silica gel with different pore size or different particle sizes are used for its packing, and then the suitable solvent is passed through your mixture and the different pigments or different components get separated depending on their retention factor, retention time. So there are, for reverse phase, the coating is C8 chain, non-octyl or C18. So these are some examples. Just try to remember the what is known as mechanism and what is the stationary phase, what is this mobile phase, and just try to remember few examples. So the second type is your liquid solid chromatography, adsorption chromatography. So in this chromatography, what happen? Your mobile phase is liquid, your stationary phase is solid, and yeah, depending on the solid phase or the stationary phase, It may be of two types. If it is a three-dimensional, then it may be column chromatography. Under two-dimensional, we have paper chromatography or thin layer chromatography. And here, the phenomenon occur between the liquid and the solid surface, each adsorption. And depending upon the strength of adsorption, your retention time will be more, and the retention factor is also increased. Then we have ion exchange chromatography. This involves exchange of ion, cation, and anion between the insoluble matrix and the solution which come in contact with it. The insoluble material is carries exchangeable cation and anion is known as ion exchanger. Those carrying exchangeable cation are known as cation exchanger, and those having anion are known as anion exchanger. So before discussing this one, let's have a look on liquid solid chromatography. So this is your liquid solid chromatography. The same one. It is your, yes, this one. Just see, this is the liquid solid chromatography. Is it visible, students? This one? Okay, okay. So in this technique or method of separation of chromatography, your mixture containing component X and Y, two components are there in this mixture, and we have a silica alumina saturated solvent here, and we just added the suitable solvent here. It may be ethyl alcohol, it may be acetone, depending on your type of component present. So when the solvent is poured inside the column, then it is passed through the mixture and also passed through the silica or alumina saturated solvent, or this is very tightly packed. And if you open up the key of this column, then what happens? This solvent will go down, and a point will come when this X and Y component gets separated according to their rate of adsorption. So, for example, this green component and this violet component present in the orange mixture. Then it is seen that the green component having the less interaction with the stationary phase is each separated first, and the pink component, so violet component, which is which has more interaction, positive interaction with the solid surface. It's separated at the end. So depending upon the adsorption, the two components separated accordingly. So, so the similar way, ion exchange chromatography we have. This is the ion exchange chromatography. Let's see here. This is the ion exchange chromatography where just see here. So this is the mixture. It is put under an electric field. Then depending upon the type of ion present, the different ions get separated in this chromatography. Then we have under ion exchange chromatography, we have three ion exchangers. If it is positive ion, then it is cation exchanger. If it is negative ion, it is anion exchanger, and if it is the component or the constituent contain both the ions, it may be treated as the amphoteric ion exchanger. There is another form of chromatography which is synonymous to ion exchange chromatography and is said as ion pair chromatography. So it is a type of reversed phase chromatography and used for the separation of ionic species. In this, the mobile phase consists of an aqueous vapor containing an organic and compound, and in this chromatography neutral ion pair is written as the non-polar stationary part. So it is subsequently treated with an aqueous solution of methanol or other water-soluble oil solvents. Ionic or partial ionic compounds can be chromatographed on the ion chain alkali anion with cation. And these reagents are typically in dilute solution. The potential analytical and AC. So these are some theoretical aspects. So under size exclusion chromatography, the chromatography is looks like this size exclusion. This is your size exclusion chromatography. You see here. So depending on the size, okay, the one having a lesser size or smaller size, we will have a strong attraction towards the adsorbent or towards the stationary phase, and the bigger size components of the mixture has lesser attraction or absorption towards the stationary phase, and accordingly they are separated fast, and the smaller ions get separated at the end. Then we have the modern technique of LC liquid chromatography, that is the high performance LC or high pressure liquid chromatography, which is known as the HPCL. Sorry, SPLC, that is high performance or high pressure liquid chromatography. Then this HPLC is the column usually contain particle of size very small, that is 3 to 10 micrometer. The material may be an adsorbent or material that permit partition, ion exchange or molecular formation. The pressure generally used is around 6000 psi. The mobile phase may be composed of one solvent or a mixture of solvent with or without modifier. Now, high pressure thin-jet chromatography, that is SPTLC, has also gained prominence or popularity. So, these are some example of your chromatography technique. Okay, so these are some example of the chromatography technique, and now we will move to the next part, that will be after liquid chromatography. It is your gas chromatography. So, gas chromatography may be of two types, because in gas chromatography, gas is the mobile phase, and the mobile phase now it is in connection with the stationary phase. So stationary phase is primarily mainly of two types. Okay, it may be liquid or solid. If the stationary phase is solid, then it is known as gas solid chromatography. If the stationary phase is liquid, then it is known as the GLC, that is gas liquid. That is the base of the stationary phase, which is used to separate different component of a mixture. If it is solid, then it is GSC. If it is liquid, then it is GLC. So in GSC, the retention of the analyte is due to physical adsorption on the column material. In GLC, the separation of place takes place because of partition between the gas mobile phase and the liquid immobilized on the surface of an inner solid. So GSC is not as popular as GLC of some limitations for the former mode. In GSC, the retention time is usually large and high temperature may be required for to deserve the gases. That is, if some constituent particles from the liquid get adsorbed on the surface of the solid, then in due time what happens? These shoes. So after few times your mobile phase is spread over the stationary phase, that is your solid, and the mobile phase is gas. So accordingly the adsorption phenomenon will occur and your gaseous particles gets adsorbed on the surface of the adsorbent, that is your stationary phase, and depending upon the retention time and retention factor, different components present in the mixture get separated, and this is the mechanism involved in GSC. Also, it is the adsorption phenomenon. Similarly, in the GLC, that is your gas liquid chromatography, the mechanism involved is your partition. So here, the gas is treated as the mobile phase, and the liquid is treated as the stationary phase. And generally, two type of column are used in gas chromatography: packed and open tubular or capillary column. The chromatographic column vary in length from less than 2 meter to 50 meter. They are constructed of stainless steel, aluminum glass, or fused glass or Teflon. Open tubular column are two basic types: wall coated open tubular or support coated open tubular. So this is the construction part of your chromatogram. So this is how the gas chromatography is separated, or it can be classified into two types, that is your GSC and GLC. Then supercritical fluid chromatography. So in this chromatography, the mobile phase is the supercritical fluid, so which is having some high temperature, and it is basically it also involve basically the partition chromatography. Here also the partition phenomenon occur. So here instead of liquid or gas, we use a supercritical fluid. In order to understand the supercritical fluid, we will have to know critical temperature and pressure of a substance. Critical temperature of a substance is the temperature above which a distinct liquid phase cannot exist regardless of pressure. The vapor pressure of a substance at its critical temperature is its critical pressure. So critical temperature is the temperature above which distinct liquid phase cannot exist. That means the liquid phase is now vanishes. That temperature is known as critical temperature. And at that time, the pressure is known as critical pressure. That means the temperature of the pressure at which your your substance gets disappear. Okay, so liquid phase cannot exist is known as your critical pressure and temperature. And the temperature and pressure above its critical temperature and pressure is known as critical point. A substance which is known as supercritical fluid. So that point is known as critical point. Then we have the supercritical fluid in chromatography is carbon dioxide. So this is the fluid which is used as a supercritical fluid, that is carbon dioxide in liquid form or fluid form. And here the respective temperature and pressures are maintained, and this is also a suitable condition for your HPLC, high performance liquid chromatography or high pressure liquid chromatography. One remarkable property of supercritical fluid, which is related to the high density, is 0.2 to 0.5 gram per liter, is their capacity to dissolve large non-volatile molecules. So another property which is associated with many supercritical fluid is that the dissolved analyte can be easily recovered by allowing the solution to equilibrate with the atmosphere at a relatively low temperature. So these are some important points of your GSC and GLC with your supercritical fluid chromatography, that is SFC. So in both GLC, GSC or your SFC, only the GSC involve your absorption, and GLC and your SFC, supercritical fluid chromatography, it involves your partition mechanism. So next we have the conclusion part, because here the classification is made in liquid chromatography. One liquid is mobile phase, another liquid acts as the stationary phase. So when the stationary phase is liquid, then it is known as LLC, liquid liquid chromatography, and when it is solid, it is known as the solid liquid chromatography. So when the liquid chromatography is there, the mechanism is partition mechanism, and the mode or examples are, if it is column, it is three-dimensional. Under two-dimensional, we have normal chromatography, where your and there is reverse phase chromatography is also there. And if in same liquid chromatography, your stationary phase is solid, the phenomenon becomes adsorption, and here the same column or two-dimensional method of separation can be involved. In your ion exchange chromatography, the mechanism is ion exchange, and here we have also column, two-dimensional batch, column, or thin layer chromatography. Under gas chromatography, we have two types. That is when your temperature is your um, gas chromatography, your mobile phase is gas. Then if it is the stationary phase is liquid, then the mechanism is partition. If the stationary phase is solid, the mechanism is absorption. And in supercritical fluid, we have liquid stationary phase and supercritical fluid as the mobile phase, and here the partition will occur. Then illusion of column, just see here, this is a column, okay, and and here what happened, when suitable solvent is introduced inside the column containing the mixture, here just see, this is one column with a mixture containing X and Y, two components. And when solvent gets passed, the two components, based on their absorption, rate of absorption, they are separated one by one, and they are, and in this diagram just see, the black color X is having the lesser attraction, and Y color, that is the silver color, it may be the cement color, okay. Y, which is having the lesser absorption rate, so that's why it is off. So X having the lesser and Y having the higher absorption rate. So which one is having the lesser absorption, we'll separate it first, followed by the higher absorption one. So up to this, anyone having any problem? It is a very simple one, that depending upon the type of sample, you may select the stationary, mobile phase, and type of mechanism involved in separating the different components of a mixture. And this is one example of a column separation of two components X and Y of a mixture. And this is the plot between distance travel versus concentration, and according concentration of the solvent, concentration of the mixture, then accordingly your concentration and graph will be like this. When If we go for the analytical estimation, then we have detected signal versus time. One component moves off at a faster rate, and the other uh, travel with slow rate. The rate of zone broadening for the two species is decreased. So this is the way the two components get separated, and they are detected signal like this. And here this is the first peak, and this is the second peak. That means this is the for your x, and this is for your y. So this migration rate, this is also known as the retention factor migration rate, and this is the distribution constant. That is x in mobile phase is equilibrium with x stationary phase. So the distribution constant will be the concentration in stationary phase divided by concentration in mobile phase. So this concentration is in terms of your molarity, that is moles per liter or molar concentration. So if the chromatography is directly proportional, that is CS directly proportional to CM, that we will get a straight line. Then this chromatography may be called as the linear chromatography, because here CS is directly proportional to CM. That is when the concentration of stationary phase increases, the concentration of mobile phase or liquid phase it also remains the same. So this is how this is the most important thing, that is the retention time, and here it is the distribution with the migration rate. So under migration rate we have different parameters or aspects like distribution constant, and the second one is retention time. So retention time is the time period in which the different particles of it or different components of a mixture reside or stay at a particular point in a stationary phase or on a stationary phase is known as retention time. So the component which reside at a particular point for a longer period may be treated as they have a strong attraction or interaction between the mobile phase as well as the stationary phase. So this is, just see here. So the first one, it is the capital L, it is the length of the column, and TL is the time. Okay, and the average rate of migration of solute molecule is given by V equal to L by TR. And similarly, for the mobile phase, it is a U equal to L by TM. Just wait. Thank you, students. So, the average rate of migration of solute molecule, it is given by V equal to L by TR, where L is the length of the column and TR is the time taken for this retention, and the average linear rate of migration U equal to in the mobile phase. It is equal to U equal to L by Tm, that is at the mobile phase. That's why it is M. So Tm may be treated as the dead time, that is the last time, and it is the time required for the average molecule of the mobile phase to pass through the column. It is the average time required for the molecule to pass through the column. So after getting familiar with the term of distribution, we may write V equal to U into fraction of times solute spent in the mobile phase. The V equal to U into multiplied by the fraction of time means it is the total mole divided by, sorry, individual mole divided by the total mole of the column. So the individual mole in the mobile phase divided by the total mole of the column. So this is how your equation goes on, and finally we have the solute migration and distribution constant, that is V equal to U into 1 by 1 plus K Vs by Vm, where K is the distribution constant, that is concentration at stationary phase divided by concentration at mobile phase. So this is how your equation was derived. So the most important term is your retention factor. So retention factor, it is a factor which is a constant entity, or it is also known as the capacity factor. Capacity factor in the sense how long a component gets attached to the stationary phase, and it is depends on the adsorption or the partition or the electromigration of different components of a mixture. We may uh, we may see the equation, that is kx, it is equal to kx vs by vm, where kx is the distribution constant, is the volume of the at the stationary phase divided by volume at the mobile phase. Then we may write substituting 4.9 equation in 4.8. So here your v equal to u plus, so this k vs by vm, it is now replaced by k dash x. So this equation is now framed 4.10, and consequently after substituting the initial equation in 4.10, we will get, and after rearrangement we will get the final equation, that is k dash x equal to tr minus tm by ta. So this may be the final equation for your chromatography, that is your tr and tr. Then selectivity factor, that is separation factor. Retention factor is known as the capacity factor. Selectivity factor is known as the separation factor. So separation factor alpha equal to ky by kx. It is also known as the separation factor or selectivity factor. Both are same. If a column having two solute x and y, then alpha may be um, determined, or it is equal to ky by kx, where ky is the distribution constant for the some more strongly retained species y, and kx is the distribution constant for more rapidly eluted species. So this is retained, that means the retention time is more. It is eluted, that means it is the retention time is less. So alpha equal to, in terms of k dash y by k dash x. So accordingly, your alpha may be calculated as alpha equal to try minus tm by trx minus t. So this is the shape of the peak. Just depending on your different equations, or the chromatogram, we have different type of peaks which are obtained in chromatography. Then we have a new equation in your theoretical plates, that is n equal to L by H, where n is the number of plates or plate count and H is the plate height. L is the length of the column. So the number of plate means number of segments and H is the height of the segment. So just see here, this is the time versus detector response. This is from your advanced chromatography peak. So this is the peak we have. So this is the sample injection baseline, and this is the mean position of this peak, and this is the retention time. That means for this time, this component gets attached to the stationary phase. This is the peak height we have, and this is the half of the height, and this is the total width is W, and this is the half width, W half. So this is how a peak of chromatogram can be described with Gaussian illusion and all parameters by using or by calculating n and tr, that is retention time and your number of plates n. So this is a very basic equation. Just try to remember this one. That is T n equal to 16 ER by WB square, where TR is the retention factor and WB, it is the width of your peak, maximum width of your peak. Then tangent, if we draw tangent, then your W2 is the distance between intersection of this tangent. The other way, W half, the width measure halfway between the baseline. Then n equal to 5.54 TR square by W half. So this is one mathematical equation. Just try to remember this one. So rate theory. So this is the rate, that is the U versus H, linear flow rate versus H. We have the liquid chromatography and gas chromatography. As we know, the gaseous particle moves faster than the liquid particle. So that's why the gaseous curve is at the top and liquid curve is at the bottom. So for the time being, I am just taking uh, 5 minutes of break, and you all are instructed to take some water, and after some refreshment we will again come back. So for 5 minutes, let's have a break. Thank you, students, for your patience. Then we have the eddy diffusion term A type, which is a multi-part term. The column is packed with particles of various sizes and shapes arranged in an irregular manner. As the carrier gas flows through the channel of the packaging, it is divided into many streams. So this is one of the packaging format in different chromatographic techniques. Then there is a equation that is A equals to 2 lambda dp, where your lambda is the dimensionless parameter depicting the irregularity of packing, and dp is the diameter of the particle. Then your longitudinal diffusion term we have. So all these terms are related to your packaging method. Okay, so how different type of particles gets packed inside a column or inside a your GLC, okay, GLC or GSC. So in this longitudinal diffusion term, we have, this is the second term in the equation, arises because of longitudinal diffusion of the solute in the gas phase. Some of the solute molecule tends to diffuse along concentration gradient. Thus, a solute band will broaden as the molecules spread into regions of lower concentration ahead of the band and behind it. And one equation, that is B equal to 2 into gamma into dm, or B by mu equal to 2 gamma d m by mu, where B is gamma or y is the correction factor, and your this is the diffusion coefficient at the mobile phase, and dm is the diffusion coefficient for solute in the gaseous phase. So these things are there. Then non-equilibrium in mass transfer term, which is known as Cu, and this is the concentration at the liquid phase divided by concentration of the gaseous phase in your GLC, because in GLC liquid phase is the stationary phase and the gas phase is the mobile phase. So that's why it is concentration at liquid or mobile phase divided by concentration at, concentration liquid or stationary phase divided by concentration at mobile or gas phase. So according to Henry's law, this concentration L by concentration G equal to K, where K is a constant quantity. So then when we plot one, that is a concentration versus the distance, then this type of plot will come, and just go through these things. Then we have the Van Demeter plot or zone broadening. So this is the your effect of different factors discussed earlier, and this is known as Van Demeter plot. From the Van Demeter plot depicting the effect of carrier gas, velocity on the factor affecting the plate height. A is not affected. So just go through these things. These are some explanation regarding different peaks in your chromatography experiment or technique, and how you are will interpret the concentration versus the distance covered, the concentration versus the retention time or the retention factor, which are the important parameters to know the interaction between the liquid mobile and the solid phase. The column should be packed with smaller particles. The column diameter should be narrow. The thickness of the liquid layer in the column should be minimized. The gaseous mobile phase, the longitudinal diffusion can be lowered by reducing the temperature. These are some important points in your GSC or GLC. Then resolution of the chromatogram or chromatography peak. The resolution is capital R, and if the mixture contains two components X and Y, Then this is an example of that is a written resolution will be 7.5, sorry 0.75. That is this is the resolution, and if it is 1.0, this is how your different resolutions are made from the time versus detected signal. Then we have another equation, resolution is equal to delta D by W x by 2 plus W y by 2, because this is the width of the peak of the x component, and this is the width of the peak of the y component, and this is the distance between the x and y, and accordingly your R is calculated from this formula. Then we have the summary part is here. So this unit is all about your different mechanism, different stationary phase and mobile phase, the mechanism of absorption, mechanism of partition, mechanism of chemical bond, van der Waals interaction. All these things are there between the stationary and solid phase, and accordingly your chromatogram or chromatography experiment is carried out to separate different components present in a mixture. So now this unit is now completed. So in this unit, if anyone having any problem or anything you wish to share or ask, you now the platform is open for 2 to 3 minutes. Then we will move to the next unit. So Foreign Saw, Vijay Lakshmi, Sahu, Jitendra Kumar, anything you wish to ask or any doubt. So this is all about separation of components depending on their absorption towards the stationary phase, depending on the partition towards the stationary phase, and the detention time, detention factor, migration terms are there, and different type of packaging. All these the basic things are discussed in your unit 4. If no questions is there, then we may move to the next unit. It is all about your gas, sorry, liquid column chromatography. So in this chromatography, this is liquid column chromatography. That means it is a three-dimensional chromatography experiment. And here, the liquid it is acts as the mobile phase, and the solid phase, the stationary phase may be liquid or solid. If the stationary phase is solid, then the chromatography is named as LSC, that is liquid solid chromatography. If the solid stationary phase is liquid, then it is termed as liquid liquid chromatography. So in liquid column chromatography, we have two types, that is liquid solid chromatography or liquid liquid chromatography. Then experimental setup, then the choice of stationary and mobile phase in different uh, chromatography, that is your liquid solid and liquid liquid chromatography, and how the development techniques, frontal analysis, displacement development, illusion analysis, basic aspect of high performance liquid chromatography or high pressure liquid chromatography was introduced in the modern era. So these things I will discuss in this part. So the first one is your liquid column chromatography. Under this we have two chromatography techniques, that is liquid solid chromatography LSC, where a solid phase is the stationary phase, and in liquid liquid chromatography, here the liquid is acts as the stationary phase, and in the first one LSC, adsorption is the phenomenon, and in LLC, partition is the phenomenon between two liquids. So directly I am just moving towards the liquid solid chromatography. This one. So in liquid solid chromatography, as we know, this is an adsorption phenomenon where the column is made up of solid particles, and here when the mobile phase is spread over the mixture by a solvent, a suitable solvent, Then the different components gets adsorbed on the surface of the stationary phase with the different adsorption rates, and depending upon their adsorption, they are separated uh, accordingly. That means the component which is adsorbed strongly with the stationary phase or the surface of the adsorbent, that component will separate at the end, and the component which is loosely bound or loosely attached to the surface of the adsorbent, that component will separated early or fast. Then it is your alpha equal to x by y a by x by y t, where alpha is the separation factor and x and y are the two components, and where adsorbed phase is A divided by the ratio liquid phase. That means it is the adsorbed phase divided by the liquid phase. Similarly, we have the liquid-liquid chromatography, where partition phenomenon is the mechanism. So in liquid-liquid chromatography, somewhat it is liquid partition chromatography. So liquid-liquid chromatography is based on the separation of the solute by the differential partitioning between two immiscible phases. This usually involves a stationary phase coated on an inert solid support, normally silica gel, and an immiscible mobile phase. Most commonly, the stationary phase is more polar than the mobile phase in some circumstances. However, it is advantageous to reverse the roles so that the stationary phase is less polar. This variation is known as reverse phase partition chromatography. This is already discussed that when the stationary phase is more polar, it is your normal phase, and if it is less polar, it is your reverse phase. The process of liquid chromatography is similar to simple batch extraction between two immiscible liquids in a separator funnel. A successive series of such extractions forms the basis of counter current distribution, which is more efficient than simple one-stage extraction. However, liquid-liquid extract chromatography is many times faster and more efficient than counter current extraction. This is the result of large interface between moving and stationary phase. So in LLC, equilibrium distribution of solutes between the mobile phase and stationary phase, it is the partition coefficient that is being calculated or determined by the term K, which is also known as the distribution coefficient or partition coefficient. For practical chromatography, it is necessary to be able to predict a particular solvent-solute relationship in order to obtain the required separation of a mixture. The distribution of a solute between two phases is also defined in terms of capacity or retention factor K. The different terms and concepts of the theoretical plates and theoretical have already been discussed in Unit 4. So this is the experimental setup. Just see this one. This is the experimental setup we have. So in this part we have this is the column we have, and this is the syringe by which your sample or your mixture is injected into the column, and and here it is the mobile phase reservoir, and which is get injected into this column, and after passing through the solvent, different your different components get separated on the basis of different partition coefficient, distribution coefficient value. So this separation of components one by one, they will be recorded, and they will be detected at the detector, and they will be recorded at the recorder, that is the monitor screen which is there in your chromatograph. Similarly, we have the equipment type 2. Just see here, this is number 1, it is a mobile phase reservoir here. It is a mobile phase. Number 2, it is the slurry device, where a slurry is prepared with silica gel or alumina. And number 3, it is your lamp for heating device. Number 4, it is the pump. That means the mobile phase gets pumped by number 4. Then this is the pressure monitoring device. 6 is the pump. 7 is the filter and pre-column. 8 is the pre-column. 9 is the column. It is the column chromatography. 9 is the column. 8 is the pre-column. 10 is the pump. That is between column and pre-column. And here the pump 10, it is pumped up the slurry or the mixture from the 8 to 9, that is pre-column to column. 11 is the injection port. 11. 12 is the column thermostat, where the temperature is maintained. 13 is the detector and 14 is the recorder. So this is a sophisticated liquid chromatographic setup where two pumps are used, or 2 to 3 pumps are used to uh, create a pressure and to flow, or to allow to flow this mobile phase reservoir through this column. And after the movement of the, or the flowing of the solvent to pre-column to column, the different components get separated on the basis of their partition position. So just try to remember and sketch out the schematic diagram of this chromatographic, sophisticated chromatographic, liquid chromatographic setup. Then here the equipment, all the uh, parts of the setup is well described. The mobile phase reservoir, I just read out, it holds 1 liter of the mobile phase. This reservoir is made up of stainless steel, which is inert to most mobile phases and is not subjected to breakage. Many different forms of reservoir have been used. So this is your mobile reservoir. So pump, it is number 4, pump. So it is used to create a pressure and pumping of the system from it will extract the mobile phase content to the pre-column through filter and different pumps. So it creates high pressure are required. Pumps are group of 2 major: mechanical pump and the pneumatic pumps. So just pneumatic pumps in that constant pressure, and mechanical pump is which is the constant flow rate. A filter is there which generally filter the particulate material and allow the slurry or the liquid phase inside the pre-column. So pressure monitoring device, this is serial number 5. Sample introduction device is there, for where there is a septum is there which is used to introduce the sample inside the device. Then column, we have 2 columns here, pre-column and for your main column. So the sample is allowed to pass through the pre-column. Then by using the pump number 10, the pre-column content is now moved to the main column, and accordingly the separation was carried out. There is a thermostat which maintains the temperature between the temperature difference of 0.2 degrees centigrade, because this is a very sensitive apparatus with a very high market price. So detectors, in liquid chromatography, the ideal detectors should have high sensitivity, good precision, predictable response to all solutes. It should be unaffected by changes in temperature and carrier flow. It should not contribute to extra column band broadening. It must be non-destructive of the solute. two types of detectors are in use in liquid chromatography: the bulk property or general detector, and solute property or selective detector. So bulk property detector measures a change in some overall physical property of the mobile phase plus that of the solute. The solute property detector is sensitive only to solute. So there are two types of detectors: solute property or selective detector, or bulk property or general detector. So bulk is the let us we have a solution. The upper part is known as surface and the lower part is known as the bulk. So whenever the bulk content or bulk property is detected, then the detector may be termed as the general detector, or where the solute property is detected, it is known as the selective detector. So column packaging, we have dry packaging of rigid solid material using tap fill procedure, slurry packing technique for column hard gel, or slurry sedimentation method for soft gel. So there are three column packing methods. Okay. So after this we have choice of stationary phase, stationary as well as mobile phase. If your chromatography is liquid solid column chromatography, then for the stationary phase we may use some uh, solid components for our stationary phase, like alumina, activated alumina, silica gel, carbon magnesium oxide, magnesium carbonate, hydrated calcium silicate, talc, silver sulfide, oxide, activated clay from bentonite, fuller's art, sucrose, or powdered cellulose. So all these chemicals or chemical compounds may be used as the stationary phase for your liquid solid chromatography. So if you are having adsorption type, then according to the pH, that is acidic, basic, or neutral environment, the stationary phase may be silica, magnesium silicate. They are may be used as the acidic, and alumina can be used in both acidic and basic side. For non-polar adsorbent, graphite carbon, which is a strong adsorbent, or so this you are advised to remember 2 to 3 examples of this category. Then according to the surface area, you may use carbon, you may use silica gel, you may use alumina, depending on the type of component you are wish to separate from a mixture. In particle size, so depending upon the particle size, we have different mass, that is silica with 100 to 200 mass, 200 to 400 mass, 1000 mass. So all these different sizes silica are available in the market, and depending upon your requirement and your application, you are advised to use the stationary phase accordingly. Then activation and regeneration of adsorbent, if your stationary phase is required to be activated, then accordingly you are used your stationary phase. Then stationary phase liquid column chromatography, that means here your one liquid is acts as mobile phase and second liquid is acts as the stationary phase. And here there are two types of things are there, that is your hydrophilic one, that is it is attraction towards water, and reverse phase, that means it is polar, and in reverse phase your stationary phase is less polar or non-polar. So depending upon your the application and your requirement, some pre-columns or post-columns are there, and the liquid which is used as the stationary phase in liquid chromatography maybe organic coating is a monomolecular, organic coating unimolecular. These are some examples of or their commercial names are there here. Durapack, Bondpack, Radiac, Permafage. So these are some commercial names. The solvent evaluation technique, in situ coating procedure, solvation filtration technique, equilibration technique, so all these things are there. Support for liquid partition chromatography. We have it should be chemically inert, it should display good wettability, it should consist of particles as identical as possible, which allow the most uniform and reproducible packing. It should have large enough surface to retain the stationary phase as a thin uniform film. Porous support generally meets this requirement. It should allow the column to have an acceptable pressure drop as regard to the mobile page. It should have sufficient mechanical stability. It must not grind during column packing. Impregnation of stationary phase, regeneration of support material. We applied for routine analysis for preparative purposes. It must be relatively cheap, easily available, and format generation. So next one is the mobile phase selection in liquid column chromatography. So we have first one is the liquid solid chromatography. It is here it is written. So for mobile phase selection, we have, and so it is the solvent. Okay. So N-pentane, isooctane, petroleum ether, cyclohexane, cyclopentane, carbon tetrachloride, xylene, isopropyl ether, toluene, benzene, ethyl bromide, ethyl sulfide, chloroform, methylene chloride, ethylene dichloride, triethylamine, acetone, dioxane, tetrahydrofuran. This is a very commonly used solvent on the mobile phase in a liquid chromatography. Ethyl acetate, methyl acetate, nitromethane, acetonitrile, dimethyl sulfoxide, N-propanol, ethanol, methanol, ethylene glycol. So here the solubility parameter delta is there and solvent state epsilon 0 is also mentioned here. So depending upon their polarity data as well as their solvent strength, you are you must selectively choose the solvent or mobile phase accordingly. When your frontal analysis, in this analysis, a large sample is treated with solvent is passed through a short adsorption column, which gets analyzed with continuously until its composition is identical with part of the original sample. Then we have the displacement development. So displacement development has the advantages of being able to accommodate large sample and giving sharp separations. So it depends on the competition between solute for the active site of the adsorbent and is only really effective in separating very strongly adsorbed material. Then lastly, we have the illusion analysis. So illusion analysis is the most common technique in chromatography. Employing illusion analysis, complete separation can be achieved. This technique is being widely used for quantitative analysis. A relatively inert solvent is used in large quantities to transport the component down the column. So this is a plot between your concentration of the solute versus your frontal analysis, displacement development, and illusion analysis. So this is a frontal analysis where one is the illusion curve for A alone. So if we have a three component system, then number two is for your B alone, and three is the three as C alone. So we have a concentration of solute versus frontal analysis. And this is the mobile phase versus solute concentration. This is a displacer, and this is the three components we have. So this is just an example of some separations. Then we have the mobile phase and components here. This is the mixture, and we have a two component system. And if the illusion analysis is there, by passing some light, then we may see the different components with the this is the column. Okay, so when the light is passed through this column, and we have the illusion of separation of different components. The see the first one, the two components are merged. The two components just touch each other, and at the end the two components are separated. So this is the illusion dilution. Then the concept of high performance liquid chromatography is there, which is now in modern days. This is a very advanced tool for separation of your components of emission using your liquid chromatography technique, and this was introduced in 1966. And it is characterized by a long, narrow column packed with a very finely powdered spherical particle, operated at a high liquid pressure and possessing a continuous monitoring facility for the column effluent. So, in HPLC, there should be non-volatile metal can be handled, ability to operate long column at near optimum solvent velocity throughout their length. The nature of mobile phase can be varied to produce either stepwise or gradient emission or both. So in Unit 8, we will briefly discuss the SPLC in details. So these are some applications of the liquid chromatography and liquid solid chromatography as well as liquid chromatography. So several interesting separation of columns with the metal ion, isomer of cobalt, vitamin B12 and metal beta diketones have been achieved. Then this is the application, that is sample separation, steroid, pesticide, vitamins, pesticide like DDT, DDT, linden, endrine, aldrin. These are all can be separated. We may separate the barbiturates containing hexobarbital or your barbitals, then catecholamines, plasma, urine, formaldehyde in air, polycyclic aromatic hydrocarbons, your oxidiostat in poultry feedstuffs. So these are all can be separated. The components can be separated using LSC or LLC. So in LSC we have the absorption phenomena, and in LLC we have the partition phenomena. So at the end, we just completed the two units today. That is the Unit 4 and Unit 5. So we have 5 to 10 minutes remaining to for wind up this class. If you have any question or anything, you may ask. And in the examination, LSC or LLC will come as long question, which will carry 10 marks. So under LSC, you may write the absorption phenomenon, and in LLC, you may write partition phenomenon. So, so the if no questions are there, so let's wind up the session. So thank you to all for the patience hearing, and we will meet tomorrow for the third class, and we will discuss the Unit 6 of your MCH course of PGDSC program. So thank you to all.
Ini kalau